Okay, now the (2009-16) document has a series of questions about balls on two ramps. One ramp with a greater slope than the other. The ramps join. It's sort of a flat V at this point. Each ramp is 30 centimeters long. So we ask questions about what happens. Let's say the first question is, if we release a ball here and a ball here at the same time, where are they, or where is this ball at the time this ball reaches this point? Now, you might first ask, how do we know that this ball gets there first? Well, the slope of this ramp is greater than the slope of that ramp, so our intuition tells us, our experience with slopes, that we're going to speed up faster on this ramp than we will on this ramp, so this ball will get there first. If you take the information given in the statement of this situation, it tells you that the slope is 0.06 here, 0.04 here. It also tells you that the slope, that the acceleration of the ball down the ramp is going to be equal to the slope times the acceleration of gravity. Now that's something that only applies if the slope is pretty small. Okay, a lot less than 1. Okay, well, 0.06 and 0.04 turn out to be sufficiently less than 1. It's a very good approximation. You multiply the acceleration of gravity by the slope, you get the acceleration of an object moving without impediment under only the influence of gravity and normal forces on the ramp. And we'll understand soon how those forces work. Okay, we conclude then that the acceleration of this ramp has a greater magnitude than the acceleration on this ramp. So, which one gets to V quicker? Well, people say it gets to V gets to the crux of the V, the point where the two ramps intersect, more quickly on the left ramp than on the right ramp. Again, because it's steeper, that's intuitive, that's experience, that's good, but that's not physics quite. Okay? It's an intuitive notion that needs to be tested or analyzed. Okay, well, we can test it, and we can test a bunch of ramps, and we find that the steeper ramps, yeah, under similar circumstances, result in greater accelerations. And we never get a case where that's not so. Again, if the ramps are otherwise identical and the thing going down the ramp. Okay, that still doesn't prove that it can never happen. And we actually never can prove that it could never happen. But we explain. Okay, we explain through analysis. Now we've got to analyze forces and free body diagrams and stuff, and we haven't gotten there yet. But having done so, we've got a theory that explains why that seems to be the case. Okay, now, if you want to apply the physics, you can say that, well, from the information I've given you, without having to analyze everything, take the information I've given you, the acceleration on this ramp is 0.06 times the acceleration of gravity. The magnitude of the acceleration over here is 0.04 times the acceleration of gravity. We have greater acceleration here, so we have greater acceleration slope times g, in the same distance from rest. So we get a situation where this kinematic equation that everybody should be familiar with, having completed assignments for Chapter 2, applies. Okay? And this situation, the first situation, both balls are at rest. Okay, so our displacement, our position minus our original position, is initial velocity times t. Well, that's just 0 if initial velocity is 0, plus 1/2 the acceleration times t squared. Well, in that case, if t is bigger, 1/2 acceleration times t squared is bigger, so our displacement from our original point is bigger. So this ball goes further. That's an argument that you can give based on Chapter 2. Okay, now let me digress to what we're doing here. I have an uncomfortable feeling that mastering physics is giving you too many chances and too many prompts. Now I could reduce that, but I don't want to do so. People are doing well with it. And you're going to learn what you learn from mastering physics. But can you fly on your own? Mastering physics, you've got an autopilot that keeps taking over for you and helping you correct things. Now, the sequencing of the problems, the interactive, the adaptive nature of the thing is excellent. So I'm not slamming mastering physics, but I have a question. Does mastering physics prepare you to solve problems without its help? And that's what we're trying to probe here. So you're going to have a series of questions for homework. Okay, and the questions are at this document on the assignments page. Okay, so first question, second question, this is the first question. Second question, how far apart are they at the instant this ball reaches the crux of the V? Well, I went ahead and solved this incorrectly because I did a calculation in my head and didn't carry my units in my head. I didn't pay attention to my units. So figuratively, I crashed my spacecraft into Mars, and when my boss finds out about it, which he probably already has, he's going to yell at me really loud. Okay, and if that's the worst of it, I'm lucky. Okay, now, you're going to get to correct my errors, but the errors are just, it's not a trivial error to not use the units, but I didn't write it out. So here I'm making a case for write out every step, write it out with the units, and I'm going to require that on written work that you submit. Okay, so anyhow, how far apart are these things at this instant? Well, we can easily calculate the motion on the left ramp. We've got everything we need. So if we can easily calculate the motion, how's that going to help us? Well, what do we need in order to figure out where this ball is going to be when this ball gets here? Well, people suggested, well, how fast is this ball going? That can be determined. Okay, we're calculating the motion in the left ramp when your kinematic equations is going to tell you how fast it's moving. Okay? Well, it took a little time, but somebody finally suggested, well, we got to know how long it takes. Yeah, bingo. We know the acceleration here. We know, if we know how long it takes, we can tell how far it goes. Okay. We need to find the time it takes the ball to get from here to here. Now we're going to do this relative to an x-axis that I kind of bend in the middle. So here's our x-axis and here's our x-axis. Okay, that's not the way we usually do an x-axis. It's supposed to be a straight line, but the motion is equivalent to motion along this continuum. There's topological motion there, notion there that we don't want to get into. So just kind of accept this in the same sense that our rider moving around the arc of the circle described by the end of the beam is actually moving in one dimension. We could straighten that arc out into an x-axis and everything would still work just the same. At least as far as the kinematics of it. How far does he go and how much time, how's his velocity change, and so forth. Okay, so anyhow, our axis will go from 0 centimeters here to 30 centimeters here to 60 centimeters here. Okay, so from here to here we have uniform acceleration, 0.6 meters per second squared. We have initial velocity 0. We have displacement from here to here, 30 centimeters. Now there's x is 30 centimeters here, and x is 0 here. So what's that tell us in the equation? Well, initial velocity is 0. so our v naught t goes away. X naught is 0. X naught is where we start. That's here. Okay, it's 0, so that makes it simple. We're just going to get x equals 1/2 ax t squared, where ax is 0.6 meters per second squared. Now I decided to estimate the time, and I did something stupid. I just grabbed the numbers. I said, well, okay, acceleration is 0.6, half of that is 0.3, and this is 30 units. So 0.3 goes into 30, 100 times the square root of 100 is 10. So it's going to take 10 seconds. Now, I didn't believe that. I've rolled enough things down enough ramps to know that this is going to get there faster. But then a student whom I trust to do things well said, yeah, that's what I got. Well, I thought, okay, that confirms it. We'll go with it. And I didn't stop to think a little bit more. And if I had, who knows, if I'd have written it out, I would have gotten it. So again, I'm advocating you write things out. But we went on with this assumption of 10 seconds, and that's wrong from the beginning. Now, in a sense, that matters because we still got the right answer here, incidentally, but the numbers in the analysis were often wrong, and the 10 seconds is wrong. So what you need to do, and part of the assignment is going to be do this, but solve correctly for t. And I mentioned in the class what the solution is, but I'm sure nobody's paying attention. I doubt if anybody wrote it down because it was in the middle of a bunch of other stuff that was more important. Okay, so anyhow, we find t when x is 30 centimeters and incorrectly get this. And this is wrong. You got to use this equation with the units. Okay, I just did numbers. I never write it down that way, but I did it in my head with just numbers without thinking clearly. Not saying that if I'd have written it down I wouldn't have made a mistake, but I don't think I'd have made that mistake. Okay, so that's easy. You need to do that. Then we got to find the position of the second ball at t equals 10 seconds, or at t equals the correct result. Now when we do this, well, on the second ramp, the initial velocity of the ball is 0. The position, well, initial velocity is 0. What's the initial position? Well, initial position is here. It's not here. Here's where the initial position is 0. On this weird x-axis, the initial position is 60 centimeters. And the acceleration, ask for people, what's the acceleration? Well, they multiply 0.04 by g to get 0.4 meters per second squared. That's good, but that's only the magnitude of the acceleration. The acceleration is in this direction, which makes it negative because it's negative on our x-axis. So we have an acceleration of negative 0.4 meters per second squared. Now this is something that you should recognize. You've encountered this in the problems that you've done in the Mastering Physics. Okay, second ball then, v naught x2. Now I'm being specific. It's not just writing v naught x, I'm writing v naught x2 to indicate that's the v naught for the second ball, and it's 0. X naught 2 is the initial x position at 60 centimeters. A sub x2, the acceleration of the ball in ramp 2, is negative 4.4 meters per second squared. Acceleration is uniform, and I emphasize this. This is a step that I want to see. Now there are various ways to write this out. I didn't because I'd had to write small, but now I would accept a little note like this when you write it out. Something like this. Uniform acceleration implies I'd want to use Ke for kinematic equations, but we use that for kinetic energy. Chapter 2 equations. Uniform acceleration implies Keq, kinematic equations. I'd accept that. But I want you to continually remind yourself that you're using uniform acceleration because you've determined that acceleration is in fact uniform. Now, a lot of times you don't have to determine it because it's given. But whether or not it's given, I want to see this. And if it's not just given, I want to see an argument that tells me why uniform acceleration is, why acceleration is uniform. So this is an important step. Okay, anyhow, then we can write down our equation for x, for particle 2. X2 here, x02, v0, x2, ax2. And now we have our quantities and we can plug them in. v0, x2 is 0, so I've got a little arrow there with a 0, so I don't have to write that down in the next step. I almost did that with x0 too because x0 is often 0, and I actually wrote it down, and then I said, wait a minute, that's not true. x0 2 is 60 centimeters, duh. Okay, so be careful. If I can make these mistakes with my centuries of experience, you can certainly make them. Okay, and then I wrote this down, and this is all correct now. And then down here, instead of meters, I wrote centimeters because I knew that's what I needed. We don't do that. We don't do that. Okay, it should not have been centimeters. It should have been meters. And if I write that down in meters, I'm going to get 40 meters, right? Okay. So anyhow, if you get the units right with the 10 seconds, you're not going to get 40 centimeters. Okay. You're going to get a lot more than that. You're going to get like 100 centimeters. And even that isn't right. Yeah, maybe it is. So anyhow, if you do it with the right units, you will end up with 40 centimeters, but that doesn't necessarily come out of this. And it certainly doesn't come out if you use 10 seconds here. So do this right. I'm not going to tell you anymore. Just write it down yourself, do it right. Include the units, include the fact that you're doing meters per second squared times second squared, and that does give you meters, not centimeters. So things are all screwed up down here. Don't screw it up. Well then, the final answer is that the balls are 10 centimeters apart because this thing ends up at the 40 centimeter position, and that's 10 centimeters from where this ball is going to be at the 30 centimeter position. Now we can go on and ask questions. A really hard question. I mean, pretty hard. It's challenging. Not everybody's going to get it very quickly, and probably not everybody's going to get it. I'm not sure I would have gotten it if I was when I was taking the course. Where do these balls meet? Okay. Now going a little beyond this example that I want you to correct. If you can solve that, great. Go ahead, impress me. I'll give you some extra credit, 5 points. And remind me about that because I'll forget I said it. If you remind me, I'll remember. If you try to solve that, well, first place, the acceleration of this ball instantly changes from 6 meters per second squared to 0.6 to negative 0.4 meters per negative 0.4 meters per second squared. This one remains negative 0.4 meters per second squared. So you got to start all over with the equation on this one. And you got to be careful about what's x when t equals 0 and all that stuff. So it's kind of tricky. It's kind of tricky to set up. Now, easier questions. Where would you put this ball to release it from rest at the same time this is released from rest at the original position in order for the balls to meet at the V. Okay, that was pretty easy. I haven't said what the solution was, but if you solve it, I want you to explain thoroughly why that would be. Another question, if I want to start both balls simultaneously from the ends, but give this one a little bit of initial velocity so that it gets down here at the same time this one does, how much velocity would I have to give it? Other question, this thing rolls down the incline and the other ball isn't there, so that it rolls then up this incline. Where does it stop? Okay. And there are a number of other questions that are posed in the bullets on that first problem. I'm not going to ask people to solve every one of them. And doing that on top of the mastering physics assignments, which take about 6 hours a week typically, and sometimes 50% more, sometimes 50% less, it would be cruel and unusual to do so. But I want you to get in the habit of, or to develop the ability to give a good, complete, nicely flowing solution to a problem with all the reasoning and the equations. That takes a while to do that, so I'm not going to ask you to do many of them. I might ask you to look at only 2 bullets on this one and hand in as a written assignment, submit electronically as a written assignment. So there we have it. It's going to take us a while to develop the skill to actually present a problem and solve it in a reliable manner. And some problems are just difficult to set up. The one about where these balls meet, that was kind of difficult to set up. You got to have some experience. It's not something you do before you've had experience. Hopefully the mastering questions and activities have given you some experience, and hopefully you can then extend that into what's going to really be required when you have tests. Okay?